Welcome back to a series in dynamic programming. Today, I'm going to show you how to use the functional equation for identifying the value function. My name is Phil, and as always, the slides are available on GitHub. So, for identifying the value function, we're going to need two conditions. First, a necessary, and then a sufficient condition. Just note that the name of the theorems follows Stokes and Lucas. So in the end, I'm also going to apply the two theorems in example so that you can see for yourselves how to apply them in practice. Now, what we're interested in is solving dynamic optimization problems. Remember that we said due to the infinite horizon, we face an infinite number of constraints, which causes direct attacks such as Kuntake and Lagrange to often run into issues. Dynamic programming instead trades in this infinite number of constraints at the cost of now having a very complex unknown object, which is the value function. So if that doesn't sound familiar to you, no problem. Check out a previous video, which will bring you up to speed. If you do have watched the previous video, remember that we derived the functional equation, which you see at the bottom. And you might remember that we said it's very interesting because it imposes a very particular structure on the problem. It actually gives us some grip on perhaps being able to identify this unknown object. And so the interesting structure is that it appears on both sides. So we know that the true function needs to map into itself, we said. And this actually gave us a necessary condition, which said that for any candidate function v to be the true value function v star, we know that it must satisfy the functional equation. And this is actually what Stokes and Lucas call theorem 2 in their book. Now, so you might say, okay, well, are we done? What else do we need? Well, it does give us some grip, but not that much because, well, as you might see, well, if we have function v, a candidate function v, which maps from our domain everything to infinity, plus or minus, this always satisfies the functional equation. Because, as I said in the previous video, infinity plus anything is still infinity. And we might indeed think that infinity is the solution for some of our problems, but we certainly don't think it is for all our problems. So that's why we need a sufficient condition. And theorem 3 does give us the sufficient condition. It says that for any candidate function that is real valued, solves the functional equation, and satisfies some growth condition, then this candidate is the true value function. So let's take it step by step. The first bit is technical and just says that v doesn't itself reach infinity. It maps into the real numbers, but it still might tend to infinity. So this is not that restrictive. The second bit is theorem 2, so we know that. Now, this last bit says that not only for the optimal, but for all feasible paths, the value of the problem over the infinite horizon goes to 0. And this usually tackles the problem that sometimes if you postpone consumption forever, then you could potentially reach infinity because it's forever. And so this rules that out. So this says postponing consumption forever does not break the problem. And the next step, we're actually going to prove this. But before we can prove it, we actually need to know, well, what we have to prove. So for the candidate function be the value function, we said that the true value function is the solution to the sequence problem. So we said that, well, for some starting value cannot. This is because we assume a maximum exists. For the optimal consumption path, that's sloppy. From 0 to infinity with discounting and some utility function, and that's what, well, our candidate function needs to be equal to. And, well, since maximum exists, it's the same as a primum, so, well, this means that our candidate function must be the least upper bound, or we have to show that it's the least upper bound of the sequence problem. And if that doesn't mean anything to you, supremums or least upper bound, check out some videos on YouTube. I might put something in the description well, that's what we have to show. So let's show that a candidate function is if it satisfies theorem 3 is an upper bound of the sequence problem. So we have to show that the candidate function is larger than the sequence is weakly larger than the sequence problem, which was said that we now rewrite this in terms of our capital. Already did this in the previous video, and this emphasizes that this is an intertemporal problem. Okay. KT. Yeah. Okay. Well, so in theorem 3, we assume that the candidate function satisfies the functional equations. Means that the k naught is equal to the maximum k1, which is feasible from k naught, maximizing functional equation. But since it's maximized, we know that this must be weakly larger than the function equation for any feasible k1. K1 for any choice which is feasible. Or okay, but we know that, again, assuming that our choice might not be optimal, this is weakly smaller than, you might already see where we're going with this, then again splitting up the functional equation. So we give this a dot maybe. So this is square value function of k2 dot. And well, if we keep doing this, what we get is that this is really smaller than the sum from 0 to n. So and now how often we want to continue doing this to, well, kt, excuse me, that's sloppy again, I'm working on my handwriting, plus beta n to the power plus n, beta to the power n plus 1 of k t plus n of k, excuse me, k n plus 1. Well, and this looks like we're almost done, right? So this first part looks super close to the sequence problem. We still have this term here on the side, but well, hold on a second. This looks so much like our growth condition from theorem 3. So actually, if we now say, okay, well, we continue doing this infinite number of time, infinite into the future, we can say that, so well, for n going to infinity, which is, well, same as t going to infinity, this must be equal to 0. And when this holds, well, we just showed that a kind function is an upper bound. And now, well, we have to show that it's the least upper bound. Now, for something to be the least upper bound, we have to show that for an arbitrary epsilon greater than 0, a candidate function minus this arbitrary number is always, well, weakly smaller than the sequence problem. So which was kt plus 1, which is feasible from kt, infinite sum kt plus 1. Okay, well, so we know theorem 3 says that the function equation must hold, so we know that our candidate function k naught is the maximum k, the optimal value for k1 feasible from k naught k1 plus we enter again r candidate function, so we know that already. I can actually say, okay, well, there must be an optimal k1, and we call this k1 star, so this is exactly equal to k1 star plus beta k1 star. Well, but this also needs to hold at every point in time, so we can say that more generally, for whatever kt we have, it must be true that this is exactly equal to k, well, where kt plus 1 is the optimally chosen kt plus 1 plus v kt plus 1 star. Well, now since this is an intertemporal problem, we can bring, let's move this, well, let's keep it here for now. We can bring the beta vkt plus 1 star to the other side, kt minus kt plus 1 equal fkt star kt plus 1 star. Well, and this is still an equality, but as you see here, what we need is an inequality. So we need to, well, subtract something, and remember that we defined this value, but we haven't used it yet. So let's make use of it. We're going to say, well, I am going to move them to the other side because it just feels a bit more natural. We're going to define a delta t for every point in time, which is always greater than 0 for every point in time, and give it the special property that for the infinite sum, discounting in delta t is equal to epsilon, as you might already know from these kind of proofs, like choosing a nice type of deviation is usually very helpful for finding the desired result. Now we can say that, well, subtracting this from our left-hand side minus, well, let's not mix up the order, beta v k t plus 1 star minus delta t is smaller, strictly even, because it's strictly larger than 0, than the current period payoff. That's one way to interpret the fkt kt plus 1 if you remember our Conger example. And we can also take the infinite horizon over this with discounting, the infinite sum with discounting, I mean. Because as you might already guess, or might have already seen, this then becomes the sequence problem again. Well, again, we don't have to use the max because we said that the k star kt plus 1 star is the optimally chosen kt plus 1. So the right-hand side is correct as we need it here, but the left-hand side isn't yet. But we can actually work with this. So if we disentangle this, it says because beta to the power 0 is 1, this actually becomes vk naught minus bv k1 minus delta naught plus bv vk1. And I'm again going to move all of this. No. Going to move all of this just a little bit over so that this doesn't become too messy for you to read. Minus beta to the power 2 vk2 minus delta, excuse me, minus beta delta 1. And so if we keep doing this, what we get is, well, we can see that these cross out, and well, if we keep doing this, this becomes an infinite sum. So this is v k naught, because that remains. We have this minus n to the power plus 1 v k n plus 1 star, because each of them gets subtracted, but depending on how far we go, that will be the last one which is remaining, minus the infinite sum of delta t. But what you remember is what we defined it as here, which is going to be useful in a second, which again is the smaller than sequence problem. So this becomes v k naught minus beta n plus 1. Well, no. So if you say that, if you let n go to infinity, we know that this becomes epsilon, as we defined it here. And remember that this is our growth condition, as we used in the previous proof. So this for n going to infinity, which is the same as t going to infinity, n plus 1 v k t plus 1 is 0. So if we let n go to infinity, we actually have that v k naught minus epsilon is strictly smaller than the sequence problem, which is what we wanted to show. And this means that if the candidate function satisfies theorem 3, it is indeed not only upper bound, but is the least upper bound, aka the maximum of the sequence problem, and hence it is the value function. So now, well, let's use these two theorems in a practical example. Now, and the example we're looking at is a congruent example from the previous video with linear utility. The harvest doubles every period, so production function is 2k, and we discount future meals at the rate 1/3, and are given some starting value k naught. Okay, well, so far we've always been working with guesses at the value function, so let's make a guess at the value function here. Later you might try to get a guess at the value function either by looking at other problems or by using value function iteration. But for now, we haven't been looking at how to actually get a guess at the value function. We just have been identifying whether it's a true one. But so now let's take a guess here, because it seems that discounting is larger than our production. And actually the value of this problem is vk equal to 2k. Well, so is this the value function? Well, it must satisfy the function equation we said, which is theorem 2. And so we say that vk naught is equal to the maximum k1 feasible from k naught. And well, now f is just a linear function, so we have 2k naught minus k1 as our f function, plus, well, beta is 1/3, excuse me, and well, our value function is 2 times k1. So what's the maximum of this? Well, we can see that this is a linear function in K1. So if it wasn't, we might try to look at derivatives or something like this, but here it's a linear function, so let's look at it. This is actually 2k0 minus 1 over 3k1, so obviously the maximum is for k1 equal to 0. Now if we plug this in, we actually see that v k0 is equal to k0. Well, so the function equation holds, so that's theorem 2 satisfied. But we also need to satisfy the growth condition. We said what the growth condition is, and that for any feasible path, so of the kt, which is our candidate function, so this is 2 times kt, this must be 0 for all feasible paths. Well, okay, well, so for the lower bound of k is 0, so it's obviously true for the lower bound. But what about the upper bound? Well, what is the upper bound here? The upper bound is not consuming anything and postponing consumption forever. And this is then actually, well, if we don't consume anything, this becomes the maximum value we can reach is 2 to the power of t k naught. Is the upper bound. Well, and so does the growth condition hold for the upper bound? Let's see. So this is 1 over 3 to the power of t. This is 2 to the power of t k naught, which is equal to the limit for 2 thirds to the power of t k naught. Well, and this is smaller than 1. So indeed, for t going to infinity, this converges to 0. So theorem 3 is also satisfied, and we know that vk equal to 2k is the true value function. So, well, thank you for tuning in, and hope to see you in the next video.